Good morning. If you remember in the previous class, we had dealt with equation of continuity and equation of motion. So, we developed in both r component, theta component and z component, that is in the cylindrical coordinate, that is r theta z. We had developed, also we developed in x y z coordinate, and we also gave the equations for the spherical coordinate r theta phi, right. Now, the question comes in the last class, if you remember, in the last slides where we had given these equations of motions, that is Navier-Stokes equations. These equations were not so much visible, the reason being the color mismatch with the background was not was rather there, for which it was not properly visible, right. And besides, if we recapitulate that what was the equation, then we say that it was like this in the r component, that is rho del V r del t plus V r del V r del r plus V theta by r del V r del theta minus V square theta by r plus V z del V r del z, that is equals to mu times del del r of 1 by r del r of r V r plus 1 by r square del 2 V r del theta square plus minus 2 by r square. This also should be del 2 V theta del theta square minus 2 by r square del V theta del theta plus del 2 V r del z square minus del p del r plus rho g r. This is for the r component, right. And then we proceed. This is for r theta z, in which r component of the equation of motion is like that. Now, if we look into the other two components like theta component, then theta component looks like this, that rho into del V theta del t plus V r del V theta del r plus V theta by r del V theta del theta plus V r V theta over r plus V z del V theta del z. This is equals to mu times del del r of 1 by r del del r of r V theta plus 1 by r square del 2 V theta del theta square plus 2 by r square del V r del theta plus del 2 V theta del z square minus 1 by r del p del theta plus rho g r. This is for the theta component, right. So, if r and theta is done, then we left with the third component, that is the z component. R theta z is our coordinate. So, if we look at that, z component looks like this, rho times del V z del t plus V r del V z del r plus V theta by r del V z del theta plus V z del V z del z. This is equal to mu times 1 by r del r of r del V z del r plus 1 by r square del 2 V z del theta square plus del 2 V z del z square minus del p del z plus rho g r, right. So, these are rather all three coordinates, or rather three components of the coordinate system r theta z. And why we recapitulated? Because it was not properly seen in the previous class last slides. Again I say that this was due to the mismatch of the color with the background. So, that was not visible. However, it is rectified, and now once more reason of course is that this is the basis of the further development, further follow up of these equations. Now, it is one of the best way of knowing the anything is that until and unless you solve some problems, you identify the parts of these equations, identify individual components, and then you implement it in the problem and solve the problem. If you can do that, then it will appear that you have understood these equations, meaning of the equations, meaning of the individual components, how one component is affecting the other. These terms must be known and must be understood. So, this is the reason we recapitulated, and now we will try to solve some problems so that our understanding becomes more clear, right. So, let us go to the problem. Say, if we define the problem like this, if an incompressible fluid is flowing between two vertical coaxial cylinders and the outer one is rotating with an angular velocity of omega, then determine the velocity for the tangential laminar flow. I repeat, if an incompressible fluid, so here we are taking the fluid to be incompressible, is flowing between two vertical coaxial cylinders, right. So, we have two cylinders, one cylinder like this and the other cylinder like this. These two cylinders are there and the outer one is rotating with an angular velocity omega. So, if this is the outer one, so this is the inner one. So, inner one is fixed, outer one is rotating with an angular velocity of omega. Then determine the velocity for the tangential laminar flow, right. Now, given this problem, here we assume one thing, that the flow is steady, there is no unsteady component. Then because as we said that this is the outer one and this is the inner one is fixed, outer one is rotating with an angular velocity of omega. If that is there, then the fluid inside between these two, that is in the annular space, how the velocity profile, what is the momentum distribution, that if we find out, then we will be able to understand and use the Navier-Stokes equations properly, right. So, for this what we need to know first, what is the problem theoretically given and how it looks like on paper. Now, if we look at this, what we have given, that we have two cylinders, this is the outer cylinder and this is the inner cylinder, right. So, outer cylinder and inner cylinder. So, if this is the inner cylinder and if this is the outer cylinder, right, and if this is the center, then we have the radii as this one is r and this one is some multiple of r, say kr, right. So, if this is true, then of course, this is the outer cylinder and this is the inner cylinder, right. And we said that it will have an angular velocity of omega, right. So, if we look at the velocity component, we will look into that. This looks like this, right, where this V theta is a function of r, right. So, this and an inner cylinder has a radius of r, and the outer cylinder has a radius of a multiple of say k r. What that k is unknown, k is a constant which we do not know. So, it can be anything, twice of r, half of r, 0.3 of r, 1.8 of r, whatever value you can assign to, right. So, does not matter. So, we have to find out this. So, this problem, if again repeating that this is the outer cylinder, this is the inner cylinder, and the fluid inside is here, right. And this, what we said, this inner cylinder is fixed and outer cylinder suddenly started rotating with an angular momentum of omega. So, at steady state, what is the velocity distribution and what is the momentum profile, that if we can find out, or shear stress component, that if we can find out, then we will be able to understand how the Navier-Stokes equation can be utilized to solve this kind of problem, right. So, if we look at whatever is given, now from this problem what we understand, that number one, it is incompressible fluid. So, rho is constant, right. It is incompressible fluid, rho is constant. If rho is constant, then many factors will go out, number one. Number two, we said that this flow is, of course, we assume to be laminar, right. Why we are assuming it to be laminar? If we again look into this, this is that and this is the outer. So, the layers which are like this, right, layers which are like this, these are the liquid layers. When they are moving like this, this interaction between the layers is not there. So, that is why we assume it to be laminar. That if we assume the flow to be laminar, we assume that the density of the fluid is constant. Then if that be true, then there is no interaction between the layers. So, when there is no interaction between the layers, that means one layer with the other layer, they are not having any mutual interaction, right. They are just moving freely, and this we have depicted like this, right. Okay. Now, if that be true, from this condition we can say that V r is equals to V z. That means, there is no velocity in the r component, right. In the r direction, had there been any velocity in the r direction, had there been any velocity, then it would have mixed like this, right, which it is not, because we assume that there is a streamline like this, as it we can, right. So, these streamlines are, since there is no r component. Similarly, and if this is the r, the other one is theta and the third one is z, right. Similarly, this is one, and you just extend it like this, okay. If this is the z component, right. So, this is the z component. So, there is no vertical, there is no horizontal that flow, since r is not or r component of the velocity is not there. Similarly, z component of the velocity is also not there, that is there is no mixing within the fluid, right. So, that is what we know is to be laminar. So, like this, then another like this. So, these kind of layers are there. So, that is one layer is not mixing with the other. So, that is why we can assume, we can say that V r is equals to V z and that is equals to 0. And also here one we must say that this, since this is moving like this, now since this is moving like this one is not going and mixing with that one, right. So, this there is no velocity component in the theta direction also, this is the theta direction, right. So, there is no velocity component in the theta direction also. So, in that case we can say del v theta del theta is equals to 0, because this theta component or v theta say 1 and say this v theta of say 5 is not, they are one is over the other, there is not mixing of this v theta also, right. V theta 1 and v theta 5 we can whatever be the value remaining the same, and there is no change in the theta component in this direction, right. So, that is why we can say del v theta del theta is 0. If this is true, then if we remember that the Navier-Stokes equation which we had originally given, right. So, this is the r component, and in the r component V r is 0, first rho is constant and also it is under steady state. So, del V r del t this is also 0, del V r del t is 0, rho is constant, right. So, we can say that these components del V r del t is 0, V r is 0. So, this component goes out, right. Del V r del theta, right, del V r del theta, that is change in V r with theta. So, that can be there. So, that is why we can say rho the V theta square by r del V r del theta, del V r del theta. If there been any V r component also with the theta, right, with the theta direction, change in theta with V r, that is not also there. So, we can say since V r is 0, so del V r del theta is also 0, V r is 0, right. So, we can say this component also is not there, minus V theta square by r. So, it remains. So, it is rho V theta square by r with a negative. Now, V z is also 0. So, this component remains 0. Then this is equals to mu del r of 1 by r, since V r is 0. So, this again is 0, del 2 V r del theta square, since V r is 0, then del 2 V theta del 2 V r del theta square, that remains 0. Then since del V theta del theta, that also is 0. So, this term also is not there. Then this term del V theta del theta is also not there, and since V r is 0. So, del 2 V r del z square is 0, but minus del p del r plus rho g r is there. Similarly, this is, if that is true, then we can write that for the first equation minus rho v theta square by r, that is equals to minus del p del r. So, here one thing, the rho g r, right, rho g r, that is the gravitational g r, since R is there, we assume that GR is negligible and GR component is not there, right. So, we then get that minus rho, right, into V theta square by R, this is equals to minus del P del R, right. Rho GR is assumed to be negligible and that can be neglected. So, if this is R component, similarly for theta component we can say on the same way, since rho is constant and since it is steady state. So, we can say that del V theta del T is equals to 0, right. We also said V R is equals to V Z is equals to 0. This was our initial. Del V theta del theta was also equals to 0, right. So, if that be true, then we can write del V theta del R, right, V R into del V theta del R, that is there. So, V theta by R del V theta del theta, that goes out, then V R V theta V over R, since V R is 0, so that goes out. So, this goes out, V Z is 0, this goes out, right. V R is 0, so this also goes out, but V theta by R, del V theta by del theta, so this goes 0. So, this is 0, this is 0, this is 0, this is 0 and this is also 0. So, left side is 0, right side is mu del L R of 1 by R del L R of R V theta, right. V theta is a function of R. So, this remains. So, 1 by R square del 2 V theta del theta square. So, since del V theta del theta is 0, so del 2 V theta del theta square is also 0. So, this term goes out. The third one del V R del theta, right. So, 2 by R square del V R del theta. So, this what? This is V R, that is R component of the velocity, V R with theta, del V theta del V R del theta, right. So, this also goes out, because since V R is only a function of R. So, 2 by R square del V R del theta, okay, no, del V R del theta, this can be there, right. So, this can be there. So, second one, this del V theta del theta is there. So, theta component here 2 by R square, R is there, del V R, V R is 0, right. So, del V R is 0. So, 2 by R square, del V R del theta is also out, and Z del 2 V theta del Z square, since it is the double derivative and there is no V theta V Z component. So, that is also 0. So, we can write and remaining 1 by R del P del theta 1 by R del P del theta plus rho G R. Now, here this will be rho G theta, as I said that there will be some mistakes. So, here it should have been rho G theta, right. Now, here also theta G theta we can assume to be 0, and del P del theta, what does it mean? Physically, del P del theta. So, pressure with the theta. So, this is the theta component. So, whatever pressure is here, the same pressure is there, the same pressure is there. So, del P del theta from the physical understanding is also 0. Now, so we cannot say that del P del theta is also there. Then we get from there left hand side is equals to 0, because all these components have been 0, all these components have been 0. So, 0 is equals to mu del r of r 1 by r del r of 1 by r del r of r v theta. This is the second equation. The first equation we got there as if you remember that it was rho minus mu, yeah, this was rho v theta square, this, that is rho v theta square by r is del p del r, right. But here it is 0 mu, this is the second, and the third component if we look at is rho is constant, Vz is 0. So, and not only Vz 0, del t is also not there, that is it is not with time, changing with time. So, del Vz del t is 0, Vr is 0. So, V theta del Vz del theta, this is also 0 because Vz is 0, Vz this term is also 0, mu 1 by r del r of r del Vz del r. So, Vz being 0, this term goes out, del 2 Vz del theta square, this is also 0, del 2 Vz del z square is 0, but minus del p del z plus rho gr, this term is again here it should be rho g z, right. So, this term is there. So, we can write 0 is equals to minus del p del z plus rho g z, this is equation 3, right. So, we need to find out V theta. So, only one equation is good enough, because one unknown, others mu is known for a given fluid, right. R is known for the given diameter of the cylinder. So, if they are known, then we are unknown is V theta. So, to find out this V theta unknown, if we solve this problem, then we can say that we start with that second equation, that is 0 is equals to del r of 1 by r del r of r V theta, right. And second equation which we got, that was minus del p del z plus rho g z, this one, right. So, this one was there, and the third one which we had already shown, that minus rho v theta square by r is equals to minus del p del r, right. This, out of these three equations, let us start with the second equation, that del r of 1 by r del r of r v theta is equals to 0. On first integration, it gives 1 by r del r of r v theta, that is equals to integral constant. So, a. So, on simplification, this can be written that del r of r v theta is equals to a r, right. So, on again second integration, we can say r v theta is equals to a r square by 2 plus b, which on simplification can be written that v theta is equals to a by 2 plus b r, right. Now, we have two equations and two boundary constants, that is integral constant b and c, right. So, we have to find out what is the a and b, what is the boundary. Boundary is v theta is equals to 0 at r is equals to r, that is what we have been said, v theta is equals to 0 at r is equals to r. This at r is equals to r is, this is constant. So, v theta is equals to 0 at r is equals to r. So, in that case we can write, then the second one is the outer cylinder is rotating with an angular velocity of omega. So, we can say v theta is equals to omega k r at r is equals to k r. So, using these two boundaries and solving, we can write 0 is equals to AR by 2 plus B by R, and omega KR is equals to AKR by 2 plus B by KR. So, in that case, we have these two equations, 0 is equals to AKR by 2 plus BK by R, and AKR by 2 is equals to minus BK by R, and omega KR is equals to AKR by 2 plus B by KR. So, on simplification and solving, we can write omega KR is equals to B by KR minus BK by R, that is equals to B into 1 by KR minus K by R, that is equals to in that case we can say B is equals to omega KR by 1 by KR minus K by R. This is equals to omega KR by 1 minus K square by KR. That means B is equals to omega K square R square by 1 minus K square. So, similarly, from that equation omega KR is equals to AKR by 2 plus B by KR. So, from there we can write 0 is equals to AR by 2 plus AR by 2K plus B by KR, and omega KR is equals to AKR by 2 minus AR by 2K, that is equals to AR by 2 into K into 1 minus 1 by K. So, in that case A becomes 2 omega K over K minus 1 by K. So, V theta can be written as omega KR by K minus 1 by K plus omega K square R square into 1 minus K square into R, that is omega K square R over K square minus 1 plus omega K square R square over 1 minus K square. So, this on simplification gives omega K square R square by 1 minus K square into R minus omega K square R by 1 minus K square. So, omega K square R square minus omega K square R square over, that was capital R, this is small r, 1 minus K square R. So, this means on simplification we can write omega K square into R square minus R square over 1 minus K square into R. So, V theta is equals to the omega K square R square minus R square to 1 minus K square R. So, we have found out from the problem and understanding of the problem what is the velocity component which is acting in the theta direction, right. So, this way if you solve many problems, you try with the other one. In this case, what we have given, that inner one is fixed and the outer one is rotating. Now, you try to do that the inner one is rotating and the outer one is fixed. So, inner one is rotating, in that case what will be the velocity component in the theta directions. Mind it, there is no V here, there is no V z, because we assumed it to be laminar. So, that is why there is no V here, there is no V z, as and it is steady state. So, del t part is also not there. So, as implementing all these, you can find out how the equation of motions, that is Navier-Stokes, can be utilized. Obviously, we will do some more problem, otherwise really difficult it will be to implement and understand. Okay. So, that is what we do here for this class. Thank you.